Chapter 8, Motion. Concept of rest and motion.
Motion of an object. In everyday life, we can see motions of many objects. Flights of birds, motion of vehicles, motion of fan blades, etc. These motions are visible to us. There are some motions which we cannot perceive. For example, blood motion through veins and arteries, and motion of air molecules, etc. A body is said to be in motion if it changes its position with respective to surroundings, and is said to be at rest if it does not change its position with respective to surroundings. Motion is a relative concept. While traveling in a train, you must have observed that roadside trees, electricity poles, etc. seem to be moving backward. But for a person along the roadside, the trees and the poles are stationary. At the same time, fellow passengers in the train appear to be at rest to us. However, a pedestrian will find the train and the passengers in it moving with the speed of the train. While your train is at the station and the train on the neighboring platform departs, what did you experience? You must have surely been surprised to feel that the train in which you are sitting appears to move while it is at rest. An object may appear to be moving for one person, and the same object may appear to be stationary for someone else. Thus, concept of motion depends on the observer. Hence, we say that motion is a relative concept.
Describing motion. We need a reference point to study the motion of any object. Let us try to understand what is a reference point. If someone asks you the exact location of your school, what will be the answer? Your answer may be, it is 800 meters in north or 2 kilometers in west from your home. It will contain both direction and distance. Here, your home is the reference point. Therefore, we can say that the reference point is the point which is used as a reference to indicate the position of an object. Reference point is also known as origin. If we change the reference point or origin, the direction as well as distance of the object changes. Let us understand this by an example. Consider Mumbai as origin. Hence, Pune will be 175 kilometers in eastward direction. Now, if we change the origin to Delhi, Pune will be 1175 kilometers in southward direction. Thus, the reference point can be varied. Motion along a straight line. The simplest kind of motion is the motion along a straight line. Most motions are complex. Among these, some of them possess rotational motion, some vibrational, and some possess combination of motions. Let us learn about linear motion and concept of distance and displacement with the help of an activity. Distance and displacement.
Let us do an activity. Mark a position A on the playground. Walk from point A towards east direction up to point B at a distance of 3 meters from A. Then walk towards north a distance of 4 meters and mark the end point as C. Let's calculate first the total distance travelled by you. Distance from A to B is 3 meters and B to C is 4 meters. Their sum will give us a total distance, that is 3 plus 4, which is equal to 7 meters. Now measure the distance between starting point A and end point C. From the figure, distance between A to C is 5 meters. Now let us define the terms of distance and displacement. Distance is the actual path followed by a body between the points in which it moves. Displacement is the shortest distance between the initial and final points of movement. Hence, the distance travelled by you is the total distance travelled, that is 7 meters here. As mentioned, displacement is the shortest distance between the initial and the final points. The displacement you have undergone is 5 meters in the direction of AC.
The distance travelled by an object in motion can never be zero, but the displacement of the same object can be zero. It is because if a moving object after travelling a certain distance eventually comes back to its starting position, then the displacement of the object will be zero. Let us understand it by considering an example. A boy starts walking on a circular track having radius 5 meters from starting position A. After certain time, he reaches back to its starting point, that is A. Here, the distance travelled by the boy is given by the circumference of the circular track, that is 2 pi r, which is equal to 31.40 meters. But the final displacement is zero. We can also conclude that the magnitude of displacement is either equal to or less than the distance.
Odometer. There is an instrument called odometer present on dashboard of a vehicle. An odometer is an equipment that indicates the distance travelled by a vehicle, such as a bicycle or an automobile. Most of the cars have two odometers. One that records the total distance travelled by the car, and the other that can be adjusted manually to record the distance travelled by the car. Odometer is also used by the people who construct roads and survey land.
Let us now solve one numerical problem. 1. A farmer moves along the boundary of a square field ABCD of side 10 meters in 40 seconds. What will be the magnitude of displacement of the farmer at the end of 2 minutes 20 seconds from its initial position? Solution. Let us first convert given time in seconds. 2 minutes 20 seconds. 2 into 60 seconds plus 20 seconds is equal to 120 plus 20 seconds, which is equal to 140 seconds. If a farmer starts from point A and takes 40 seconds to move along field ABCD to complete one visit, then in 120 seconds he will complete 3 visits, reaching the starting position A. In the next 20 seconds, he will reach from point A to point C. We know that the displacement is the shortest distance between the initial and final position. So, the displacement of the farmer is given by diagonal AC of field ABCD. Displacement is equal to length AC. Let us now find out length AC using Pythagoras theorem. Length AC square is equal to length AB square plus length BC square. Length AC square is equal to 10 square plus 10 square. Length AC is equal to root 200. Length AC is equal to 14.14 meters. Thus, the magnitude of displacement of a farmer is 14.14 meters. Uniform motion and non-uniform motion.
Uniform and non-uniform motion along a straight line. Let us do an activity. Mark distance on a track. Ask your friend to ride a bicycle steadily. Note his starting point. Observe the distance travelled by him in each minute for 3 minutes. You will find the distance covered by him in each minute is equal. Ask your friend to start once again, but with slow speed at the beginning, and then increasing the speed for some time, and then applying brakes to slow down. Find the distances covered in each minute for 3 minutes. You will find that the distances covered will be different in each minute. The motion in which the object covers equal distances in equal intervals of time is uniform motion. The motion in which object covers unequal distances in equal interval of time is non-uniform motion. Example of the uniform motion is the motion of a car moving on a straight highway with same speed. While example of a non-uniform motion is the motion of a car moving on a hilly road. Let us consider an activity. The distances covered by a car A and a car B with respect to time are given. Look at the distances covered by the car A and the car B with time. We find the car A travels equal distances in equal intervals of time, whereas the car B does not cover equal distances in equal intervals of time. That is, motion of car A is an example of uniform motion, whereas that of car B is that of a non-uniform motion.
Speed.
Concept of speed. The motion of an object may be fast or slow. For example, a car travels faster than a bicycle. When we say an object moves fast, we refer to its speed. Distance traveled by a moving body in unit time is known as speed. Mathematically, speed is equal to distance traveled by a moving body divided by time required to travel that distance. SI unit of speed is meter per second. Symbolically, it is written as m/s or ms inverse. We also use units like kilometer per hour, denoted as km/h, kilometer per minute, denoted as km/min, centimeter per second, denoted as cm/s, to measure the speed. Average speed. The ratio of total distance traveled by an object to the total time taken by it to travel that distance is known as average speed. Mathematically, average speed is equal to total distance travelled divided by total time taken to travel that distance. The average speed is not the average of different values of speed taken over a period of time, as these different values of speed might not be taken over the regular time interval. Constant speed. Let us now understand about constant speed. If a body in motion travels equal distances in equal interval of time, then its speed in each time interval remains the same. Such a body is said to be moving with uniform speed or constant speed. In case of uniform motion, body moves with constant speed. Conversion of units of speed. We have seen that kilometer per hour and meter per second are the units of speed. Let us convert kilometer per hour into meter per second. 1 kilometer per hour equals to 1 kilometer divided by 1 hour is equal to 1 into 1000 meters divided by 1 into 60 into 60 seconds, which is equal to 1000 meters divided by 3600 seconds, which is equal to 5 by 18 meter per second. Therefore, 1 kilometer per hour is equal to 5 by 18 meter per second. Now, let's convert meter per second to kilometer per hour. 1 meter per second is equal to 1 meter divided by 1 second is equal to 1 by 1000 kilometer divided by 1 by 3600 hour is equal to 3600 divided by 1000, which is equal to 18 by 5 kilometer per hour. Hence, 1 meter per second is equal to 18 by 5 kilometer per hour. Speedometer. Let us now understand how the speed of a vehicle and the distance travelled by it are measured. You might have seen an equipment on the dashboard of a car or a scooter. This equipment measures and displays the speed of the vehicle in kilometer per hour at any instant of time. It is called speedometer. Mostly, all motor vehicles have a speedometer. A speedometer helps the driver to keep a track on the speed of the car and drive safely.
In rainy season, when it is cloudy, you must have seen thunder and lightning frequently. You must have surely noticed that the sound of thunder reaches after you see the lightning. Why does this happen? Well, this happens because of the large difference between the speed of sound and light. The speed of the light in air is 3 into 10 raised to 8 meters per second, and the speed of the sound in air is 340 meters per second. Due to this large difference, lightning is seen first and thunder sound is heard later. Let us perform an activity to find out the nearest point of lightning on a cloudy day. Take a stopwatch and start it at the instant you see a lightning flash. Stop the stopwatch as soon as you hear thunderclap. Let us assume that your reading is 24 seconds. Therefore, the distance d at which thunder took place equals velocity. V of the sound into time, t. Substituting the given values, we get d is equal to 340 into 24 meters per second. D is equal to 8,160 meters. D is equal to 8.16 kilometers. Therefore, the distance at which thunder took place must be 8.16 kilometers. Let us now solve some numerical examples. 1.
A bus runs with a speed of 40 kilometers per hour. How long will it take to cover a distance of 80 kilometers? Solution. Given data, speed s equals to 40 kilometers per hour, distance d equals to 80 kilometers, speed equals to distance traveled by a moving body divided by time required to travel that distance. Therefore, time taken to travel the distance equals to the distance traveled by the moving body divided by the time taken to travel that distance. Substituting the values of d and s in the equations, we get time equals to 80 kilometers divided by 40 kilometers per hour. Therefore, t equals to 2 hours. Hence, the bus takes 2 hours to travel the distance of 80 kilometers at the speed of 40 kilometers per hour. 2. Calculate the average speed of a car covering the given distances at regular intervals of an hour. Solution. The total distance covered by the car is the sum of all the distances covered. That is, the total distance travelled equals to 70 kilometers plus 69 kilometers plus 80 kilometers plus 83 kilometers. This equals to 302 kilometers. Total time taken to travel this distance is 4 hours. The average speed of the car is equal to the total distance travelled by the car divided by total time taken by the car to travel that distance. Substituting the values in the equation, we get average speed equals to 302 kilometers divided by 4 hours, which is equal to 75.5 kilometers per hour. Hence, the average speed of the car is 75.5 kilometers per hour.
Velocity.
The distance travelled by a body in given direction in unit time is called velocity. Velocity is the speed of an object moving in a definite direction. As distance travelled in a particular direction is called displacement, velocity is the rate of change of displacement with respect to time. Velocity is equal to displacement divided by time. Unit of velocity is the same as the unit of speed. Speed is related to distance, while velocity is related to displacement. The magnitude of velocity and speed will be equal if motion is along a straight line path. If motion is along a straight line path, the magnitude of velocity and speed will be equal. In other cases, magnitude of speed is greater than magnitude of velocity. As velocity is related to speed and direction, it can be changed by 1. Changing the speed and keeping direction the same. Example. Consider a ball falling freely. Here, the magnitude of the velocity goes on increasing as it comes down. Here, the direction of the velocity remains the same. 2. Changing direction and keeping the speed constant. Example. The motion of the tip of the second hand of a clock. The speed of the second hand is constant, but the velocity of the tip of the second hand changes because the direction of the motion changes all the time. 3. Changing both speed as well as direction of motion. Example. The motion of a motorcyclist in a circus, driving the motorcycle in a vertical circle inside a cage. Here, speed of the motorcycle is maximum when he is at the bottom of a circular track, while it is minimum when he is at top.
Average velocity. If an object moves unequal distances in a particular direction in equal intervals of time, or it moves equal distances in equal intervals of time, but its direction of motion changes, then the velocity of the object is said to be non-uniform. When an object moves in a specified direction in a straight line at a variable speed, then the magnitude of average velocity can be calculated in the same way as that of average speed. That is, mathematically, magnitude of average velocity is equal to the total distance traveled divided by total time taken. If the velocity of the object moving in a specified direction in a straight line changes at a uniform rate, then average velocity is given by the arithmetic mean of initial velocity and final velocity for a given period of time. V subscript AV is equal to U plus V divided by 2, where V subscript AV denotes the average velocity of the object, U is the initial, and V is the final velocity respectively. Let us now solve some numerical problems on what we have learnt.
1. An athlete runs on a circular track of length 400 meters in 50 seconds and returns to the starting point. Calculate average speed and average velocity. Solution. Given. Total distance covered is equal to 400 meters. Total displacement, which is equal to 0 meter as he returns to the starting point. Total time taken is equal to 50 seconds. To find average speed is equal to what? Average velocity is equal to what? Average speed is equal to total distance covered divided by total time taken, which is equal to 400 meter divided by 50 second, which is equal to 8 meter per second. Average velocity is equal to total displacement divided by total time, which is equal to 0 meter divided by 50 second, which is equal to 0 meter per second.
And retardation.
Acceleration. Whenever a vehicle is speeding, that is, when the speed is increased, we say that the vehicle is accelerating. What exactly is acceleration? Let us consider an example to elaborate the topic of acceleration. Sunita is pedaling her bicycle along a straight path. Starting from rest, the velocity of the bicycle goes on increasing. After some time, Sunita stops pedaling and the velocity of the bicycle slowly decreases. In both the cases, velocity does not remain constant. The rate of change of velocity is called acceleration. Acceleration is equal to change in velocity divided by time. If u is initial velocity of an object and v is the final velocity of the object attains in time interval t, then the acceleration of the object is a is equal to v minus u divided by t. The SI unit of velocity is meter per second and time is second. SI unit of acceleration is meter per second square. Examples of accelerated motion are: when body starts moving from rest and attains a velocity v in time interval t. Here, initial velocity u is equal to 0. When body moving with some velocity u comes to rest at the end of the motion, here final velocity v is equal to 0. In both the cases, velocities of the body changes. Acceleration of a body may be positive or negative. If the velocity of an object increases, then the object is said to be moving with positive acceleration. Here, acceleration is in the direction of velocity. Example: a ball falling freely under the gravity. If the velocity of an object decreases, then the object is said to be moving with negative acceleration. It is opposite to the direction of velocity. Negative acceleration is also called deceleration or retardation. Example: a ball is thrown vertically upwards, moves with a negative acceleration as the velocity decreases with time. If the change in velocity is 0, that is, either the object is at rest or moving with uniform velocity, then the object is said to have 0 acceleration. 0 acceleration is related to uniform motion. A uniformly moving body has 0 acceleration as it covers equal distances in equal intervals of time. Most bodies possess two types of accelerations. 1. If there are equal changes in velocity of the body in equal intervals of time, then it possesses uniform acceleration. A body falling freely under gravity is the example of uniformly accelerated motion. 2. If there are unequal changes in velocity in equal intervals of time, then it possesses non-uniform acceleration. If a car traveling along a straight line road increases its speed by unequal amounts in equal intervals of time, then the car is said to be moving with non-uniform acceleration.
Let us now solve some numerical problems based on whatever we have learnt. 1. A car decreases its speed from 60 kilometers per hour to 40 kilometers per hour in 5 seconds. Find the acceleration and retardation of the car. Solution. For this problem, the term speed is referred to as velocity. Here, initial velocity of car u is equal to 60 kilometers per hour. final velocity of car v is equal to 40 kilometers per hour and time taken t is equal to 5 seconds. Let us first convert the units of velocity, that is, from kilometers per hour to meters per second. U is equal to 60 kilometers per hour is equal to 60 into 5 by 18 meters per second, which is equal to 16.66 meters per second. Similarly, V is equal to 40 kilometers per hour is equal to 40 into 5 by 18 meters per second. V is equal to 11.11 meters per second. Substituting these values in the formula of acceleration, A is equal to V minus U divided by T. We get A is equal to 11.11 minus 16.66 divided by 5, which is equal to minus 5.55 divided by 5, which is equal to minus 1.11 meters per second square. Thus, the acceleration of car is minus 1.11 meters per second square. The negative sign indicates that it is retardation. So, the car has a retardation of plus 1.11 meters per second square. 2. A bus starting from a station and moving with uniform acceleration reaches a speed 50 kilometers per hour in 4 minutes. Find its acceleration. Solution. For this problem, the term speed is referred to as velocity. Here, since bus starts from a station that is from rest, initial velocity u is equal to 0. Final velocity v is equal to 50 kilometers per hour. And time taken t is equal to 4 minutes. In order to find out the acceleration, we first need to convert the unit of velocity and time in the same unit of system. V is equal to 50 kilometers per hour, which is equal to 50 into 5 by 18 meter per second, which is equal to 13.88 meters per second. T is equal to 4 minutes, which is equal to 4 into 60 seconds, which is equal to 240 seconds. Substituting these values in the formula for acceleration, A is equal to V minus U by T. We get A is equal to 13.88 minus 0 divided by 240. A is equal to 0.057 meters per second square. Thus, the acceleration of bus is 0.057 meters per second square. Graphical representation of linear motion.
A graph is a pictorial representation of variation of one quantity with respect to another quantity. Let us learn how to plot graphs. 1. First of all, draw two mutually perpendicular lines, one horizontal and the other vertical on a graph paper. Horizontal line x dash x is known as x-axis and the vertical line y dash y is known as y-axis. Their point of intersection is known as the origin. These two axes divide the graph paper into 4 quadrants. 2. Take independent variable on x-axis and dependent variable on y-axis. The name of the graph is read as the quantity on y-axis versus the quantity on x-axis, or dependent quantity versus independent quantity. For example, distance versus time. 3. Taking appropriate scale. Show the values of both the quantities on respective axes. Scale should be selected considering the maximum and minimum values of both the variables. Usually on a region, values of both the variables are taken as 0. 4. Now, plot the ordered pair x, y formed by the values of independent variable and dependent variable on the graph paper and show it by a point. Join all the points obtained in this way by a free hand. The shape of the graph thus obtained may be a line or a curved line depending on the data.
The linear motion of an object can be studied with the help of the distance time graph or displacement time graph and speed time or velocity time graph. It should be noted that when an object moves in a straight line path, the direction of motion does not change. So, for linear motion, the terms displacement and distance, speed and velocity are used in the same sense. Thus, the distance time and the displacement time graph are the same. Similarly, the speed time graph and velocity time graph are the same. Let us now proceed to learn distance time graph in detail. Distance time graph.
As discussed earlier, when an object covers equal distances in equal intervals of time, then the object is said to be in uniform motion. We know velocity is equal to distance upon time. Therefore, distance is equal to velocity into time. In an uniform motion, the velocity is always constant. Hence, distance is directly proportional to time. Let us consider a body moving with a constant speed along a straight line. Here, the body covers equal distances in equal intervals of time. The change in position of object with time can be represented on distance time graph by taking a convenient scale of choice. Time is independent variable plotted along x-axis. Distance is dependent variable plotted along y-axis. From observation table, it is clear that the body covers 7 meters for every 5 seconds. As distance d is proportional to time t, the graph of d versus t will be linear. The inclined straight line in the distance time graph shows that the distance increases linearly with time. Thus, distance is directly proportional to time. Distance time graph for non-uniform motion. In non-uniform motion, the velocity of the object is not constant. That is, the object does not cover equal distances in equal intervals of time. Such objects are said to have non-uniform motion. Consider a body moving with some speed. The distance covered by the body with time is given in table. Let us plot a graph between the distance covered and the time taken. The object covers unequal distances in equal intervals of time. The nature of distance time graph is a curve having varying slope. The curve in the distance time graph shows that the distance is increasing rapidly with time. What difference do you notice in distance time graphs for uniform motion and non-uniform motion? The differences are: in uniform motion graph, we observe an inclined straight line passing through the origin. In the non-uniform graph, we observe a curve showing the non-uniform motion of the body. In the first graph, for every 5 seconds, the body covers a distance of 7 meters, and this continues further for every 5 seconds. In the second graph, the distance travelled is not uniform. For every 10 seconds, the body covers different distances. For first 10 seconds, the body covers 1 meter. For the next 10 seconds, the body covers 3 meters. Further, the distances covered for each 10 seconds increases, giving us a curved graph. A more steeply inclined distance time graph indicates greater speed. When the object shows non-uniform motion, the nature of distance time graph is a curve with varying slope. Distance time graph for a stationary object. In this type of motion, the object does not move. That is, it remains at rest with respect to a fixed reference point. Consider a car in the state of rest, at a distance of 10 meters from the observer. The observations made by the observer while studying the motion of the car for a regular interval of time are tabulated. Let us plot a graph between the distance covered and the time taken to cover that distance. On plotting the graph, we get a straight line parallel to the x-axis. Hence, we can conclude that the car is always at a distance of 10 meters from the observer, which implies that the car is at rest.
The distance time graph can never be a straight line parallel to the distance axis. It is because a body moving in a certain direction would never cover the distance which is increasing without any change in time. In other words, a body can never move with infinite speed. Velocity time graph.
Velocity time graph for uniform motion. In uniform motion, we know that the velocity is constant. We know that displacement is equal to velocity multiplied by time. The variation of velocity and time can be represented by velocity time graph for uniform motion. Consider an object moving with uniform velocity of 5 meters per second for 25 seconds continuously. We can calculate the distance travelled by the object with the help of the graph. Time is represented along the x-axis and velocity along the y-axis. In this case, for every time instance, the velocity is maintained at 5 meters per second. So the graph plotted will give the constant velocity parallel to x-axis. Displacement can be calculated by finding the area of rectangle formed by the line showing constant velocity and the time interval. The heights PS or QR represent the velocities at time t1 and t2 respectively. The displacement of the object in time interval t2 minus t1 is given by the area of the rectangle PQRS. Area is equal to length multiplied by breadth. Displacement of the object in time t2 minus t1 can be expressed as S is equal to PS multiplied by PQ. Area formed by rectangle PQRS. S is equal to 5 meter per second multiplied by T2 minus T1 second. S is equal to 5 multiplied by T2 minus T1 meter. S is equal to 5 into 15 meter. S is equal to 75 meter. Velocity time graph for uniformly accelerated motion. In uniformly accelerated motion, velocity increases by equal amounts in equal interval of time. Let us consider a biker. The biker is pacing with an uniform acceleration. The reading of the speedometer is constantly monitored and we get the following reading. With the help of these readings, we plot a graph. The nature of the graph is a straight line passing through the origin. In uniformly accelerated motion, velocity increases by equal amounts in equal intervals of time. We get a straight line graph. Here the graph is straight line, hence the biker is moving with uniform acceleration. For non-uniform accelerated motion, velocity time graph can have any shape according to variation in velocity with respect to time. Let us determine the distance travelled by the bike between 10 second to 20 second using the graph between velocity and time. Consider a small part AB on the straight line in the velocity time graph. Draw perpendicular AD and BC at T1, which is equal to 10 seconds, and T2, which is equal to 20 seconds. A quadrilateral ABCD is formed as shown in the graph. Draw perpendicular AE from point A on BC. Area of ABCD is equal to area of triangle AEB plus area of rectangle AECD, which is equal to 1 upon 2 multiplied by AE multiplied by BE plus AD multiplied by AE, which is equal to 1 upon 2 multiplied by 10 multiplied by 16 plus 16 multiplied by 10, which is equal to 80 plus 160, which is equal to 240 meter. Hence, the distance travelled by the biker between 10 and 20 second is 240 meter. We can also calculate the acceleration by calculating the slope of the graph. Slope of AB is equal to BE upon AE, which is equal to 32 minus 16 divided by 20 minus 10, which is equal to 16 divided by 10, which is equal to 1.6 meter per second square. Hence, the acceleration of the biker in time interval 10 and 20 second is 1.6 meter per second square.
Velocity time graph for variable acceleration. Let us now consider an example of variable acceleration. A car starting from rest changes its velocity in an irregular manner. The table shows the velocity of a car at regular intervals. Let us plot a velocity time graph. On plotting the graph, we can clearly see the velocity of the car is changing in an irregular manner. Velocity time graph for uniform retardation. Let us now consider an example of uniform retardation. A car moving at a velocity of 40 meters per second comes to a stop in 8 seconds with uniform retardation. The table shows the velocity of a car at regular intervals. Let us plot a velocity time graph. On plotting the graph, we get a straight line inclined to the time axis.
Equation of motion by graphical method. Did you know motion of objects was studied by Newton and then it was summarized in a set of equations of motion? The equations analyze rectilinear motion, that is, motion along a straight line of an uniformly accelerated body. The position of such a body can be well predicted with the help of a set of 3 equations called kinematical equations. Let a body be moving along a straight line with initial velocity u. After time interval t, it attains final velocity v as acceleration a is produced. Then the set of 3 equations is given as v is equal to u plus at. 1. It represents velocity-time relation. S is equal to ut plus 1 upon 2 at square. 2. It describes position-time relation. V square is equal to u square plus 2as. 3. It represents relation between position and velocity. These equations can be derived by graphical method. 1. Equation for velocity-time relation. Consider the motion of an object having a velocity u when it is at point P at time t1. U is considered as initial velocity. Let velocity of the object go on increasing uniformly with respect to time and be equal to v when it reaches point Q at time t2. The change in velocity is at uniform rate a. Here, v is the final velocity. The time interval t2 minus t1 is taken as t. Let us consider the graph velocity time graph. The acceleration of the object is given by a is equal to velocity divided by time interval. From velocity time graph, the acceleration is given by the slope of the graph. Hence, acceleration a is equal to qr divided by t. Therefore, qr is equal to at. A. Now let us find change in velocity from graph. To find change in velocity, draw PR parallel to OS. We have QS is equal to QR plus RS, which is equal to QR plus PT. Put QS, which is equal to V, QR, which is equal to AT, and PT, which is equal to U. Therefore, V is equal to u plus at. This is a velocity-time relation. This is known as the first kinematical equation. 2. Equation for position-time relation. Let us consider the motion of an object moving with uniform acceleration a. Let s be the distance travelled by the object in the time interval t. In the velocity-time graph, the distance travelled is given by area enclosed within TPQS. Hence, distance travelled S is equal to area of quadrilateral TPQS. S is equal to area of rectangle PRST plus area of triangle PRQ. S is equal to TS multiplied by TP plus 1 upon 2 multiplied by PR into QR. Put TP, which is equal to U, TS, which is equal to PR and which is equal to T, and QR is equal to AT. Therefore, S is equal to UT plus 1 upon 2 AT square. This is the second kinematical equation. 3. Equation for position-velocity relation. The distance travelled by the object in time t under uniform acceleration is given by area enclosed within quadrilateral TPQS under velocity time graph PQ. As sides PT and QS are parallel to each other, it is a trapezium. Hence, distance travelled S is equal to area of trapezium TPQS, which is S is equal to 1 upon 2 multiplied by QS plus TP multiplied by TS. Put TP, which is equal to U, QS, which is equal to V, and TS, which is equal to T. S is equal to 1 upon 2 multiplied by V plus U multiplied by T. Equation A. From velocity-time relation, we have A is equal to V minus U divided by T. That is, T is equal to V minus U divided by A. Equation B. Therefore, using B in A, we get S is equal to 1 upon 2 multiplied by V plus U multiplied by V minus U divided by A. 2AS is equal to V square minus U square. V square is equal to U square plus 2AS. This is the third kinematical equation. Hence, from the velocity time graph, we have derived the three kinematical equations of motions, namely 1. V is equal to U plus AT. 2. S is equal to UT plus 1 upon 2 AT square. And 3. V square is equal to U square plus 2AS. We have studied uniform and non-uniform motions along a straight line.
Let us now solve some numerical problems based on whatever we have learnt. 1. A bus increases its velocity from 5.5 meters per second to 13.8 meters per second in 10 seconds. Find its acceleration. Solution. given initial velocity u is equal to 5.5 meters per second. Final velocity v is equal to 13.8 meters per second. Time taken t is equal to 10 seconds. To find acceleration a, from the first equation of motion, we have v is equal to u plus at. Substituting the given values, we get 13.8 is equal to 5.5 plus a into 10. 13.8 minus 5.5 is equal to 10a. 8.3 is equal to 10a. 8.3 divided by 10 is equal to a. 0.83 meters per second square is equal to a. Thus, the acceleration of the bus is equal to 0.83 meters per second square. 2. A bike has a uniform acceleration of 2 meters per second square. What distance will it cover in 6 seconds after the start? Solution. Given initial velocity u is equal to 0, time t is equal to 6 seconds, acceleration a is equal to 2 meters per second square. To find the distance covered, that is s, from the second equation of motion, we have s is equal to ut plus 1 by 2 at square. Substituting the given values, we get s is equal to 0 into 6 plus 1 divided by 2 into 2 into 6 square. S is equal to 36 meters. Thus, the distance covered by the bike in 6 seconds is 36 meters. 3. A car with an initial velocity of 4 meters per second accelerates uniformly at the rate of 0.12 meters per second square over a distance of 150 meters. Calculate the final velocity of the car. Solution. Given initial velocity u is equal to 4 meters per second. Acceleration a is equal to 0.12 meters per second square. Distance s is equal to 150 meters. To find the final velocity, that is v, from the third equation of motion, we have v squared is equal to u squared plus 2as. Substituting the given values, we get v squared is equal to 4 squared plus 2 into 0.12 into 150, or v squared is equal to 16 plus 36, which is equal to 52. Therefore, v is equal to root 52, which is equal to 7.21 meters per second. Thus, the final velocity of the object is 7.21 meters per second. Uniform circular motion.
We have observed the motion of an electric fan, hands of a clock, spinner in the washing machine, spinning top, a cyclist moving in a circular track. All these are examples of circular motion. Motion of the body, which covers equal distance in equal interval of time, is called uniform motion. When velocity of the body changes with time, then the body is said to be accelerated. The change in velocity is due to change in its magnitude or direction of motion, or both. Let us consider an object moving with uniform speed on a square path ABCD. The object has to change its direction of motion 4 times to reach again to the starting point. 2. Let the object now be moving along a regular hexagonal path A, B, C, D, E, F. The object has to change its direction 6 times to complete one round. 3. Similarly, if the object moves along a regular octagon A, B, C, D, E, F, G, H, it has to change direction of motion 8 times to complete one round. 4. As the number of sides of the path increases, the object has to turn more often. Now, if we increase the number of sides indefinitely, the shape of the path will approach the shape of a circle. Therefore, a circle can be considered as a polygon with infinite sides where each side will resemble a point. Thus, an object moving with a velocity of constant magnitude along a circular path, the only change in the velocity is due to change in direction of motion. It is an accelerated motion. Uniform circular motion can be described as the motion of an object in a circle at a constant speed. Let the object travel along the circular path with velocity v. Let the object complete one rotation in time t. The distance traveled by the object in one rotation is equal to the circumference of the circle, 2 pi r, where r is the radius of the circular path. Then, velocity is equal to circumference divided by time. V is equal to 2 pi r divided by t. Examples of uniform circular motions are: 1. Motion of the earth around the sun. 2. Motion of the moon around the earth. 3. Motion of the electron around the nucleus. To determine direction of uniform circular motion, let us perform an activity. Take a piece of thread and tie a small piece of stone at one of its ends. Move the stone in a circular path with constant speed by holding a thread at the other end. Now, let the stone go by releasing the thread. Can you tell the direction in which the stone moves after it is released? Repeat this for a few more times and release the stone at different positions of the circular path. Does the direction in which the stone moves remains the same or not? If you carefully note, on being released, the stone moves along a straight line, tangential to the circular path. This is because once the stone is released, it continues to move along the direction it has been moving at that instant. This shows that the direction of motion changes at every point when the stone was moving along the circular path. Nonetheless, it is accelerating due to its change in direction. Thus, the direction of velocity of an object at any instant performing uniform circular motion is along the tangential direction to its position at that instant.
Let us now solve one numerical problem. 1. A cyclist is traveling at 6 meters per second around a circular track. If the radius of the circular track is 110 meters, calculate the time taken for one round. Given pi is equal to 22 by 7. Solution. Given speed v is equal to 6 meters per second. radius of circular track R is equal to 110 meters. To find time taken for one round, that is t, the speed of a body moving along a circular track is given by v is equal to 2 pi r divided by t. So, t is equal to 2 pi r divided by v. Substituting the given values in the above formula, we get t is equal to 2 into 22 into 110 divided by 7 into 6. T is equal to 115.2 seconds, which is similar to 115 seconds. The time taken for one round, t, is equal to 115 seconds.